Great, thanks, Tom. Okay, yep, so just to give an outline of my talk. So first of all, I'm going to talk a little bit about the background to what I do and why I'm interested in XPS with DFT. I'm then going to talk a bit about the theory of what I'm doing, so in a particular DFT code called Madness, and I'll explain kind of what's special about that code. And then I'll go through some different examples of what we can do, first of all, looking at amino acids, and then looking at disordered systems, both for a molecule and a particular phase of gallium oxide. So first of all, about me. So as Tom mentioned, I'm particularly interested in electronic structure and DFT in particular. So I've worked on a range of DFT codes. So I've got this kind of Venn diagram of DFT interests. So I started my PhD working on the one-step code, and what's kind of special about that is that it's a linear scaling DFT code. So it can treat very large systems, much larger you can get with kind of the normal cubic scaling codes. I then moved on to work on big DFT, which has in common with one tip that's linear scaling. So again, we can look at kind of thousands of atoms. But then what else is special about big DFT is it uses a particular type of basis set called wavelets, which I'll talk a little bit about today. And then kind of I moved on to looking at Madness and more recently the MRChem code. So I'm mostly going to be talking about Madness in this talk. And this also kind of uses a slightly different flavor of wavelets known as multi-wavelets. And so I'll tell you today why that's particularly useful for core states. So I'm interested in kind of large systems, the kind of things you can do with linear scaling DFT, different types of spectroscopy. So particularly I'll be talking about core states today, but also I'm interested in kind of valence and excited state spectroscopy. And then I'm also interested in kind of a range of applications from molecules to solids, and we'll see a bit of both today. So first of all, why XPS? So X-ray photoelectron spectroscopy. So for those of you who are not familiar with this technique, the basic idea is that we have some incident X-rays, and these excite some electrons, in the core case from a core state out into the vacuum, or in valence XPS case from the valence states out into the vacuum. So this is a useful technique because we can directly probe occupied states. It gives us information about local chemical and coordination environments. We can learn things about bonding, and we can also learn about the electronic structure. And so the kind of things you get out in the valence case, we kind of have this spectrum with different features that we try and interpret in some way to tell us about the electronic structure. And then in the core states, we kind of get different peaks associated with particular core orbitals. So typically, once we've measured the XPS, or say I don't do the experiments, but once my collaborators have measured the XPS spectra, for valence XPS, it's very common now to kind of pretty much in all cases, people interpret the results based on theory. So typically this involves density functional theory, where we apply photoionization cross sections to a projected density of states. And this isn't perfect. There are some kind of ambiguities about projection schemes, what the cross sections might be for certain states. But this is a pretty well kind of validated and common approach. You also can go beyond DFT to do things like GW, but I'm purely talking about the DFT level today. For core XPS, on the other hand, typically people just interpret the spectra based on kind of reference spectra. So for relatively simple materials, or where you've kind of got some reference systems which work as a good comparison, this works pretty well. But in some cases where we have quite complicated systems, or we have complicated spectra for some reason, this is very challenging or even potentially impossible to interpret just kind of based on this comparing to reference spectra. So ideally, we'd like to be able to predict our spectra, and in my case, using DFT, though again, there are other kind of approaches available, for example, using GW. And this kind of gives us new opportunities for extracting more information from core XPS. And this is a kind of process that's become more and more common over the past few years. There's been lots of nice examples, particularly for molecules, but also more and more so for solids as well. So really, if we want to kind of understand complicated materials, particularly like the disordered ones I'm going to show you here today, we want to be able to predict our core spectra. And this also enables us to do a direct comparison between theory and experiment. So it's not just useful for interpreting experiment, but it could also be useful for validating our theory, as I'll show in the example of gallium oxide later on. So how do you actually calculate core XPS with DFT? Well, our key quantity are the binding energies. In my case, I'm only really interested in the relative binding energies, which makes life a lot easier because the absolute values are much harder to predict. We need to take into account things like relativistic effects, but these kind of more or less cancel out in the relative case, so I'm going to ignore those today. There are a number of different approaches, even at the DFT level. So the simplest is just to use what we call the Koopmans approach. So here we just take the negative of the core eigenvalue energies. So this has the advantage that it's cheap, so you can just do kind of one calculation at the all electron level and you get all your core binding energies. And for some systems, this works very well. So in those cases, that's great. We can get away with using Koopmans, but it does only give you the initial state effects only, and sometimes this is not enough. So an alternative approach, which is popular for good reason, because it often works very well, is to do what we call the DeltaSCF approach. And in this case, we have an explicit core hole. So we remove electron from the core state that we're interested in, and then we calculate our binding energy as the difference between this energy of the final state with the core hole and your kind of initial ground state. So this works very well for many systems. We get to include the final state effects, so we're going beyond Koopmans, but it is more expensive because we have to do one DFT calculation for every core state that we're interested in. So if we're going to use this approach, we ideally want to kind of make the cost as low as possible for each of those calculations, particularly in large systems where we might have lots of core states we're interested in and therefore lots of calculations involved. So there are a couple of decisions you need to make when doing these kind of calculations. So the first is the basis set. So for molecular calculations, it's by far the most common approach in DFT to use a Gaussian basis set. So these are all electron typically, so we get access to the core states that we're interested in. But core excited calculations in Gaussian basis sets are often quite difficult to do. So we typically need to go to larger Gaussian basis sets than we would normally use, which can make the calculations a lot more expensive. Or there are some kind of alternative approaches where we build a basis set that's kind of custom designed for core states. And this can work quite well if you have one of these basis sets that exists for kind of the type of molecule that you're interested in, but it requires maybe a little bit of extra knowledge about the system. An alternative approach that's typically used for solid state calculations is a plane wave basis set. So if we're interested in core states with plane waves, we don't typically have access directly to the core states. So either we want to do something like core hole pseudopotentials, which I'll talk a little bit more about later, or we might do something like the projector or augmented wave method. So these are kind of slightly indirect approaches of getting access to the core state, unlike in the Gaussian calculations where we just treat the core states explicitly. But on the other hand, we have the advantage that everything converges systematically. So we can just increase our basis set cutoff and we get more accurate results. So we don't need to worry too much about kind of custom building basis sets to treat the core states. So as I mentioned, these kind of two approaches, we have a slight difference in the way we treat the core electrons. So I mean, in the all electron case, this is kind of conceptually straightforward, easy to understand. We don't have to worry about the accuracy of kind of imposing some approximations, but this is relatively expensive, although we can directly impose a core hole. In the pseudopotential approach, this tends to get a bit more complicated. The accuracy might not be quite as good, but generally in most cases I've seen it's still very good, so that's not typically a problem. It's cheaper, so we can do larger systems, and also particularly interesting for me, periodic boundary conditions, so silicon solids. But generally we have to generate a pseudopotential with a core hole, so there might be some kind of expertise involved here. So one of my questions is, can we combine the advantages of these kind of two approaches? Can we have an approach where we have direct access to the core states, but we also have some kind of systematic convergence? And the question is, if so, how do we do that? So instead of using Gaussians or plane waves, I want to tell you a little bit about wavelets, which is the basis that I told you I use in big DFT, and it's also kind of related to what we do in madness. So why do we need another basis set? Why do we care about wavelets? Well, different wavelet families have different properties, but among the properties that they can be localized in real and Fourier space. So we get the real space localization that Gaussians have. They can be orthogonal, and they're also systematic. So similar to the plane wave basis set, we have kind of a handful of parameters that we can systematically converge to increase the accuracy. And we can also have analytic operators. And then there's one kind of extra bonus property, which is kind of adaptivity, also known as multi-resolution. So what does this mean? So this is kind of a schematic of the simplest possible wavelet family you can define, which are the Haar wavelets. So we have these red functions here, which are scaling functions. And kind of the useful thing here is that we can take scaling functions on a finer resolution and combine them together to make a scaling function on a coarse resolution. We can also define a second type of function, which is this blue function, which is the wavelet. And so we can also combine scaling functions and wavelets to get a scaling function on a different resolution level. So this is kind of a very flexible formalism, which allows us to go between different resolution levels by combining either scaling functions or scaling functions and wavelets in different ways. So we use these in big DFT, but instead of the kind of simple Haar wavelets, we use these least asymmetric Dolbesch's wavelets of order 16, which have the nice feature they can exactly represent 8th order polynomials. So we have our red function as the scaling function and the blue function as the wavelets. So in big DFT, we have a single grid with a fixed grid spacing, and then we have 2 resolution levels. So kind of far from the atoms where the wave functions are smooth, we have a coarse region which just has a scaling function on each grid point. And then close to atoms where the wave functions are more quickly varying, we have a scaling function and 7 wavelets, and this we kind of call the fine region. So this is useful for inhomogeneous systems. It's efficient. It's also an open source code that has a range of boundary conditions, and we can do linear scaling so we can look at large systems. So this kind of wavelets give you a lot of advantages for a DFT code. But big DFT is pseudopotential only. And if we're interested in core states, okay, we could generate some core host pseudopotentials, but really I'd like a code that has access to the core electrons explicitly. So instead of doing wavelets in the kind of Dolbesch's wavelets approach, we're going to look at something that we call multi-wavelets. So multi-wavelets, instead of having a smooth basis, we use discontinuous basis functions in a discrete domain. So if we look at the 1D case, we're basically going to divide our 1D domain into boxes. So these are kind of at different levels n, you kind of have increasing number of boxes, which we kind of label with the indices L. We then want to put some functions in the boxes, so our scaling function equivalent, and here we're going to use Legendre polynomials as an example. So we have Legendre polynomials of different orders, but these are discrete, so we kind of cut them off at the edge of the boxes. And then our basis set is basically consists of a set of these Legendre polynomials, and we scale and shift them to fit in the boxes. So we have Legendre polynomials going up to so kind of k Legendre polynomials that live in these different boxes at the different levels n. So that means if we want to increase the basis set size, we don't have a single parameter. We can either increase the order of the Legendre polynomials, so increase k, or we can increase n, so kind of decreasing this effective grid spacing. And in practice, we usually do both at once. So why is this useful? So unlike in big DFT, where we have these fixed 2 grid resolution levels, in Madness, we have local refinements. So we increase the accuracy only where we need it, but to as many levels as needed. So if you imagine if your wave function is varying very strongly in this corner of the system, you have a finer grid resolution. And if it's kind of varying smoothly, we don't need these extra grid points over here. So we're kind of optimally refining our basis set to kind of give us the best balance between accuracy and cost. And more than that, this whole process is done automatically. So all the user needs to do is kind of specify their target accuracy, and the basis set will kind of refine automatically to meet that threshold accuracy. And when we put this into a DFT code, what that gives us is a molecular all-electron DFT code, which can get up to kind of micro Hartree accuracy if you push the basis set fast enough. And so to achieve this, we have, for example, in the water molecule case, we adapt the grid separately for each of the orbitals to kind of keep this balance between accuracy and efficiency. So this is quite a nice formalism. We've got explicit access to the core states. We can get very precise energies, but we want to do a little bit more than that. And so the next kind of step that we're going to do is also make use of the fact that we have pseudopotentials implemented in Madness. So there's a particular type of known as HGH-GTH pseudopotentials, which are the same as what we have in big DFT. So we've tested them quite well and know that they're generally quite accurate. But in Madness, we can also combine the all-electron and pseudopotential in a single calculation. So the only kind of parameter you need to choose is which atoms in your system you want to treat at the all-electron level and which ones you want to treat at the pseudopotential level. So this is something that you could do, for example, in a Gaussian code, but unlike in a Gaussian code where you might have to tune the basis set in each case or your choice of effective core potential, which is kind of equivalent to pseudopotentials. In this case, the grid refinement is going to automatically refine for you. So in the all electron regions or where you kind of have a core state, you'll get a better kind of higher refinement of the grid to kind of balance out that accuracy. And what this means is that we can have high precision or access to core states for the atoms where we care about the core states. And for those where we don't, we can kind of save some cost and just treat them as pseudopotential. So how does this work for the DeltaSCF approach? So we have 2 kind of options. We could just do the pure all electron approach where all atoms in the system are all electron. But this kind of often gives rise to a problem that happens in kind of Gaussian codes as well, which is known as core hole hopping or delocalization. So if you imagine you have kind of 2 carbon 1s orbitals that you're interested in, you put a hole in one of the carbon 1s. Sometimes in various cases, that hole might kind of hop to the other carbon atom, or it might kind of delocalize across the 2. And so this can lead to kind of poor convergence and in some cases wrong answers. So there are ways around this problem, or tricks to try and get it to converge to the right state. But a kind of easier, more intuitive approach that we can do in MADNESS is to do what we call the mixed mode, where only the atom that we're exciting the core electron on is treated at the all electron level, and all of the others are treated at the pseudopotential level. So that means we only have core states on the atom where we're kind of trying to excite the core electron. So it's not possible to have this core hole hopping problem. So this makes the convergence generally smoother, although maybe not always quite as smooth as we would like. But we at least kind of don't end up on this wrong state, so we don't have this problem. It's also cheaper because by removing many of the core electrons from the system, we're kind of reducing the number of electrons we want to treat. So this makes the cost overall cheaper, which is important, as I mentioned, in DeltaSCF, where we might have to do lots of calculations if we've got lots of core states of interest. And the error induced by doing this is generally very small. So we've tested, for example, with methanol, and the difference in the core binding energies between this mixed approach and this pure all electron approach is kind of the order of 0.01 electron volts. So much kind of smaller than the other sources of error we care about for the relative binding energies. So this approach works quite well, but the question is, what does it look like for actual real systems? So the first example I'm going to talk through is the case of amino acids. So first of all, we looked at simple amino acids, so glycine, alanine, and serine. So these are kind of useful test systems because they've been studied quite a lot, both experimentally and with theory. So we kind of understand what should happen with the binding energies. We can also explore things like conformational effects. So for example, here are different conformers of alanine. And you can see if we compare for these 4 different conformers for the carbon 1s binding energies, the oxygen 1s binding energies, there's some kind of small differences, particularly between kind of the first and the next 3. But we actually measured the spectra, and we're also interested in what happens for solid state amino acids. And in the solid state, the amino acids are in this phytoionic form. And we also kind of want to know what the effects of hydrogen bonding are, which can be kind of quite important on the core binding energies. But the problem is MADNESS only works for molecules. So we don't have periodic boundary conditions, which means we can't do molecular crystals. We did try and do some clusters of amino acids, but because of the kind of charges that arise in this phytoionic form, this gets pretty difficult to kind of build a sensible cluster. And you can see if we just calculate a gas phase phytoion, which is not really stable, so probably not wise anyway, but you also get kind of completely the wrong binding energies for the carbon atoms. So what we'd like to be able to do is to actually calculate them in the crystals. So here we kind of went back to the idea of doing a plane wave approach with core hole pseudopotentials. So for example, for the carbon 1s, you generate a pseudopotential with a missing electron for the carbon 1s orbital. And this is quite easy to do in the CASTEP plane wave DFT code because there's an on-the-fly pseudopotential generator. So you could just kind of tell it, remove an electron at the start of your calculation. So we did the CASTEP calculations for the solids, but we also used the supercell approach to calculate the core binding energies for molecules with CASTEP and compared them to the MADNESS results. And actually we found very good agreement. So this was kind of quite reassuring that at least for the relative binding energies, which are what we're interested in, whether you use core hole pseudopotentials or whether you use MADNESS, you get pretty similar results. So this is kind of a nice confirmation of both approaches. We also, so then just comparing with experiments, so here you can see in the colored lines are the DFT calculated results for CASTEP using the PBE0 functional, and the dots are the measured spectra. And you can see that we get very nice agreement between the two. Of course, for this system, we already knew very well which of these peaks correspond to which atoms in the simple amino acids. As I mentioned, this is a kind of a very well-studied system. So next we wanted to kind of look at something where it was maybe a little bit more complicated, so perhaps less well understood. So we then moved on to looking at a selection of aromatic amino acids. So on this slide, I'm just kind of focusing on tyrosine. And so one of the things we kind of discovered that for systems that are kind of aromatic, the binding energies become much harder to interpret. So typically your intuition in XPS is often kind of based on looking at nearest neighbor effects. So what do we think that the nearest neighbors are likely to kind of have on the core binding energy shifts? But for aromatic states, this kind of breaks down a bit. So we also saw some quite dramatic differences between the Koopman's approach and the DeltaSCF approach. If you look at kind of the molecular gas phase kind of molecules. So we found that kind of interestingly that the Koopman's approach was more in line with the chemical intuition, whereas the DeltaSCF in some cases was kind of qualitatively completely different. We also found that kind of going from the gas phase to the solid, we get some quite big changes kind of in the ordering of the binding energy peaks. So just kind of relying on your gas phase intuition or your understanding of gas phase doesn't really give you a good interpretation of the solid state either. But it was also kind of hard to rationalize the results just by looking at the values for tyrosine. So what we did in MADNESS was to kind of do a systematic series of molecules where we're kind of systematically removing functional groups to try and understand what were kind of these effects of what was nearest neighbor, which were the functional groups that were added on that made some difference. And this kind of allowed us to build up a much clearer picture of what was going on with the core binding energies in these aromatic solid amino acids in the solid state. And also just to show kind of again with the PBE0 case for the solid state, our spectra agree reasonably well with the experiment. So this is working pretty well and enabled us to kind of interpret the binding energies for these kind of complicated aromatic systems. So the next example I want to look at is 2CZPN. So what is 2CZPN and why is it interesting? Well, this is a molecule that falls under a particular class of organic LED molecules. So these are organic LEDs based on a process called thermally activated delayed fluorescence. So this is interesting. So kind of because current OLEDs are typically based on molecules containing heavy metals. So like this example here, you can't see it's got an iridium in the center. Often they have iridium or platinum or other kind of heavy metals. And this is not particularly good from a sustainability point of view. Whereas it was kind of relatively recently discovered that molecules based on this TADF process can be both efficient and organic. And what is that this TADF actually involves? So it's basically if we have a small enough singlet triplet splitting, we get reverse intersystem crossing between the triplet and the singlet level. And if this singlet triplet splitting is kind of small enough, this can be thermally activated. And this kind of enables us to get this delayed fluorescence. So this results in kind of a very efficient OLED device potentially, and we can have purely organic emitters, so we avoid this problem of the heavy metals. So 2CZPN is an example of one of these molecules. So of course, kind of one of the main parameters, although not the only one that we're interested in predicting to try and understand TADF OLEDs is the singlet triplet splitting, and that's something else I've been working on, but I'm not going to talk about today. But for the purpose of this talk, one of the kind of interesting things to know is, like many other types of OLED, these structures tend to be very disordered. And so both this disorder and the effects of this environment can have a strong influence on the singlet triplet splitting, but also not so much work has been done on understanding the effects of this disorder for ground state properties. And so XPS kind of gives us a way of potentially understanding how the disorder works at the ground state. But also for kind of core XPS, we potentially have a way of probing this kind of disorder on a more kind of local level, because we can map to particular atomic sites. So we looked at a structure of 2CZPN, so starting from a molecular dynamics generated structure. And this structure has a lot of disorder in it, so both kind of rotational disorder, so also these two angles are not necessarily equal, coming from this MD trajectory. We also kind of other distortions, so our bond lengths are kind of distorted or have some disorder in them. These particular different, as we refer to them as subfragments, have some non-rigidity effects. So there are various things that might affect both the valence XPS and the core XPS results. So rather than trying to calculate all 500 of the molecules, we also defined a way to extract 42 representative molecules. So you can see these 42 molecules we're looking at, and you can see the different variations in the angle that we have. You can see that the kind of in cases where the angles are not the same as well. So these are kind of the subset of molecules we're looking at to try and understand the disorder. So we also wanted to kind of separate out these different effects. So we defined kind of 3 levels. So in the first case, we just took the gas phase relaxed molecule and we rotated these 2 angles kind of together in tandem, keeping them the same. So to try and understand the effects of rotational disorder. We also extracted molecules from the cluster and then imposed some rigidity on these planes. So kind of basically forced them to be planar. And then we also extracted the molecules from the cluster without making any changes. So we have these rotated, rigid, and extracted molecules to understand our different levels of disorder. And so the first thing we did was just to calculate the frontier orbitals. So here we have PBE for all 500 molecules, PBE just for these 42 representative ones, and then PBE0 for the representative ones. And kind of there are various things going on. So I mean, the functional is important for the absolute values, but we can see that we have some nice trends with torsion angle, particularly for the rotated molecules, but we also can see this kind of disorder just involved in the spread of values we have both for the HOMO, the LUMO, and the gap. But at least the kind of overall trends are relatively well preserved just by looking at the 42 molecules compared to all 500, So this kind of reassured us that looking at the 42 was okay, which is particularly important for the core binding energy calculations, where we have to do kind of quite a lot of calculations because it's kind of one calculation per core excited state. We also kind of could more or less draw the conclusion that the torsion angle is important, whereas the non-rigidity is pretty negligible, the effects of that. So we're really kind of, the rotational disorder matters kind of the most out of the three levels. So then we also calculated the valence XPS spectra and compared this to what we've measured, although I should say that the sample that we were measuring for the 2CZPN was actually kind of more crystalline than disordered. So this possibly isn't a completely fair comparison. But at the top, we have just the kind of projected density of states and then the weighted projected density of states for the gas phase relaxed molecule compared to the experiment. So if you kind of look closely, you can see that we're overestimating some of the nitrogen S peaks. And we've also kind of have a too small bandwidth overall, but otherwise there's actually a reasonably good matchup between the different peaks in the theory and the experiment. And then more kind of interestingly, we also looked at these kind of different, the relaxed compared to the rigid, compared to the extracted molecules. And we can start to see at the higher binding energies some of the effects of disorder. So we get kind of bigger differences between the relaxed molecule and this kind of average over the extractive molecules, which is in blue. But in the valence XPS, it's pretty hard to kind of disentangle these effects, already understand what's important. So this is why the core XPS is also useful to look at. So the first thing we want to check is whether our level of theory is appropriate. So we compared here the Koopmans to the DeltaSCF approach, and we found that for most of the atoms, they have a reasonably similar trend. But for these carbon atoms in the cyano group up here, you get something quite different between Koopmans and DeltaSCF. So for this particular system, if we want to kind of get a balanced picture of the binding energies, then using DeltaSCF is important. And we also compared PBE to PB0, in this case, just looking at the relaxed molecules. And particularly for the nitrogen 1s, we do kind of get quite a big difference between the functionals, but because of cost, we're just going to kind of focus on PBE. Although we did kind of do some extra comparisons just to look at the nitrogen to kind of understand the effects that made. And in general, the trends are pretty well preserved between the two functionals. So looking at the trends of the DeltaSCF calculated core binding energies here for the rotated, the rigids and the extracted molecules, we can see that there's quite a strong sensitivity to torsion angle. So we have kind of some opposite trends between the two kind of nitrogen 1s binding energies. And then for the carbons, we also have kind of this variation in both the qualitative trend and in also kind of the strength of dependence on the torsion angle. And then for the rigid and the extracted ones, we also kind of get even greater variation in these core binding energies, as we would kind of expect based on the extra levels of disorder present. How does this compare to experiment? So just like with our aromatic amino acids, we found we can't really rely on a nearest neighbor interpretation. So if we look at our experimental spectra at the bottom and kind of the peak fitting, for the carbon 1s, we kind of end up with 3 broad carbon peaks, but these are kind of hiding these different kind of combinations of carbon atoms, which were not necessarily the ones we expected before doing the calculation. We also kind of find that the nitrogen 1s binding energy peak peak separation is overestimated compared to experiment. So this is mostly due to the fact that PBE is not really doing a good enough job for this system. But we also then kind of see some subtle effects if we compare the relaxed to the rigid to the extracted molecules. So for the carbon, it's pretty subtle, but for the nitrogen, we see that actually disorder is having kind of a much bigger difference, particularly in this kind of peak separation. So it would be kind of interesting to see what would happen if we would also measure the XPS on a kind of disordered sample. But in either case, we kind of, using this approach, we get to see kind of the effects of the disorder on kind of the spread of core binding energy as compared to just looking at the gas phase relaxed molecule, for example. So this approach enables us to kind of learn some new things about disorder in 2CZPM. So for the final example, I'm just going to move to the solid state. So we're looking here at a material kind of called gallium oxide. So gallium oxide is an ultra-wide bandgap material, so bandgap somewhere around 5 eV. So this has a lot of potential uses in applications like power electronics or solar cells. And there are a number of different polymorphs of gallium oxide. So here just showing the alpha, beta, and epsilon phases. And so a collaborator had looked at the electronic structure of these using both theory and experiment. And they had some samples for the gamma phase, but found that this was a bit of a challenge for a theory. So why is this a challenge? So if we look at the neutron diffraction structure, which was looked at by Playfed and collaborators, and if we look at the unit cell, so this is a 54 atom, not quite stoichiometric cubic cell. And the reason this is kind of complicated is because we have this 4 different gallium sites, so 1, 2, 3, and 4. And the 1 and 2 sites have quite high occupancies, and the 3 and 4 sites have very low occupancies. So we have some kind of challenge already with these occupancies. This may seem a bit obvious, but for those of you who may not be so familiar with DFT, we can't treat fractional atoms with DFT. So whereas in our crystal structure, we can just, in the kind of the diffraction refinement, we can just apply these occupancies to the sites. In DFT, we either need to have an atom or not an atom. So we need to kind of make some decisions about which of these sites to occupy. And there are lots of different ways to do this, given the kind of number of sites that are present in the cell. So to kind of summarize why this is challenging, so already, as I mentioned, our unit cell is not stoichiometric. We have these small occupancies. We kind of also know from other experiments that there's both short and long range disorder in this system. And we need many atoms. So kind of the smallest stoichiometric cell that we defined has 160 atoms. So it's 1 by 1 by 3. But if we wanted to look at the long range disorder, we would potentially need to go even bigger. So we could use kind of a structure generation approach in DFT. So we can assume that lower energy structures are more likely to be stable and so probably more realistic. But the 160 atom cell is already too large for most crystal structure finding algorithms. So similar materials, people have kind of done an exhaustive search by looking at all the possible occupancies, but we have far too many combinations to do that in this system. We could just generate them randomly, but this is quite inefficient and potentially leads to some unphysical structures. So what we decided to do instead was to combine random structure generation with a simple machine learning approach. And this means we can screen more potential structures than if we were to just do DFT. But we can do this process. We can kind of assume, as I mentioned, that low energy DFT structures are more stable, and these are the structures that are more realistic. But we also want some way of validating these results compared to experiment. And our way of doing this is to look at XPS. So first of all, just to kind of briefly mention the machine learning model. So as I mentioned, this is really very simple. Perhaps we might even call embarrassingly simple. So the idea we take our structure here, we're kind of assuming maybe different atom types, gallium and oxygen, for example, and we define some radius around a particular atom as shown in purple, and we just cut out all the atoms within that radius. So this is what we call kind of an environment of this purple atom. Each of these environments has an associated energy, and then the energy of our system is just the sum of the number of times each environment appears times the energy of that particular environment. So this is a relatively kind of standard approach. But then the embarrassingly simple part comes in as to how we actually compare environments. And we basically just decided to compare the number of neighbors only. So completely throwing away anything about the actual positions. We basically say that if the number of gallium atoms in one environment is equal to the number of gallium atoms in another environment, and the number of oxygen atoms is the same in both environments, then these are the same environment. So in these two cases, we have 3 orange atoms, 3 green atoms, they're the same. In this case, we have a different number of orange and green, so they're different. So it really is very, very simple, but actually works surprisingly well. So we went through kind of multiple steps, which I'm not going to talk about, for kind of generating structures to try and kind of balance out our data set and had to refit the model. But our final model, we have a pretty good accuracy. So if we compare our DFT energies across the structures that we calculated to our predicted energies, you can see our error is of the order of 7.5 millieV per atom. So we were pretty happy with this for kind of screening, bearing in mind that we don't really want to precisely calculate the DFT energies here. We just kind of need to know roughly which ones are likely to be lower and which ones are likely to be higher as our first kind of step. So to summarize the screening process, so we generated of the order of 1 million structures and screened them with this machine learning approach. And then we had about 1,200 converged, so this should be PBE calculations that we calculated with PBE. Well, what was actually interesting to note is that many of these initial structures were metallic, which, given that gallium oxide is an ultra-wide bandgap material, was not exactly what we were hoping to see. But just to give you an idea of kind of the range of energies we produce, so we had kind of structures where just 2 of the gallium sites were occupied, some where 3 were occupied, and some where all 4 were occupied. And we had this kind of relatively large spread of energies. So once we kind of finally calculated these 1200s, also DFT calculations, we took the 5 lowest energy 2-site, 3-site, and 4-site structures, and then as kind of a benchmark comparison, we selected 5 2-site, 3-site, and 4-site structures randomly as well. The hope being that our lowest energy structure should give a kind of better comparison to experiment than our randomly selected ones. So we then relaxed these 30 structures using big DFT and PBE. This gives kind of pretty similar structures to if we use, for example, a more expensive functional HSC in the VASP code. And kind of perhaps more reassuringly for all of the structures, at least a band gap opened up during relaxation. In many cases, still rather smaller than we would like, but at least none of them were metallic after we relaxed them. And just to give you an idea of what these structures look like, so you can see some of the disorder. So our overall lowest energy structure was this 3-site structure. So we don't have any of the gallium 4 sites occupied. Our occupancies kind of don't exactly match the experimental ones, but they're kind of the right ballpark. Our lowest energy 4-site one was only ever so slightly higher in energy, and this is kind of a bit closer to the experimental occupancies, but not quite enough gallium 3 atoms, for example. And then we also have our lowest energy 2-site structure, which is a little bit higher in energy. You can also see kind of some of this short range disorder in the system. So we have kind of distortions around our tetrahedra and octahedra, as well as kind of the site occupancy disorder. So our first thing was to calculate the valence XPS. So here we use the CAS step code with PBE. So we cross-section weighted the projected density of states to compare to our measured valence XPS. And what we have on the low energy, on the left here is our low energy structure. So the colored lines are the theory, the black dots are the experiment, both for soft X-rays on the top row and for hard X-ray measurements on the bottom row. In the middle, we have kind of our medium energy structures, and then on the right, we have our higher energy structures, so these kind of randomly selected ones. And the first thing to kind of note is that our low energy structures, as we hoped, give a much, much better agreement with experiment than our randomly selected ones. So this kind of gives us some reassurance that this DFT-based screening approach was a good idea. And in fact, you can see in some cases, these are kind of quite drastically wrong compared to experiments. So there's really quite a big difference between the low energy and the high energy structures. But we don't really, we're not kind of really able to discriminate between the 3-site and the 4-site structures. So we can see that some of the 2-site ones are a little bit worse with their agreement with experiment, but we kind of can't really see if the 3-site or the 4-site are better. So although this is kind of useful for telling us that, yep, the low energy structures are definitely better, we can't necessarily say whether, yeah, it's definitely kind of a 3-site structure or 4-site structure, or whether one structure might be slightly better than another. And then we also then looked at the core states. So here we did DeltaSCF with our core hole pseudopotentials with CAS-step PBE functional. So because of the kind of cost here, so we have 160 atoms in our system. If we want to calculate the core binding energies, we need to do 160 calculations per structure. So this is a lot more expensive. So we didn't look at quite all of the 30. But we have in the middle here the lowest energy structures, which you can see agree very nicely with experiment, both for the gallium and the oxygen, whereas our higher energy randomly selected structures are quite drastically different. So these don't agree very well with experiment at all. So the same story as we saw with valence XPS, which is nice. If we also kind of look at the details of the core binding energy, so this is for the lowest energy 3-site structure, you can see we still get quite a spread both in the oxygen binding energies and the gallium ones. And what's happening when we kind of go to these higher energy structures is we have a greater diversity of binding energies, which is probably coming from the fact that we have a greater diversity of environments. So this is kind of telling us that some of the environments that we see in the randomly selected high energy structures are leading to core binding energies, which are not showing up in the experiment. And so that's kind of confirming that those environments are not particularly realistic and they're kind of not present in our actual gallium oxide sample. So we can kind of see though that we needed to calculate the core binding energies of both the different sites, but and kind of the different atoms with their slightly different local chemical environments in order to get kind of this good agreement with experiment. So that brings me to my summary. So I've talked about our multi-resolution approach that we use in MADNESS. And so by combining our multi-resolution, multi-wavelet basis set with a mixed all-electron and pseudopotential approach, this allows us to do accurate DeltaSCF calculations for molecules where we avoid some of the problems with core hole hopping, which can happen in a pure all-electron approach. So this allows us to look at kind of complex molecular systems like this 2CZPN well, we have both kind of a combination of aromatic effects, which make the results hard to interpret, as well as kind of this effective disorder, which leads to our spread in core binding energies. And in cases where we've done the comparisons, this actually agrees very well for the relative binding energies calculated with DeltaSCF with core hole pseudopotentials in the plane wave CASTEP code. And so this is an approach that works very well for solids like the gallium oxide example, or the kind of amino acids that I showed earlier. And this allows us to kind of cross-validate, for example, structures, random or kind of low energy structures generated using a machine learning model to kind of see which ones are more realistic. And so in the kind of low energy realistic structures, as I showed you, these agree very well with experiment, whereas the high energy ones don't. So basically our kind of XPS calculations give us a way of kind of providing that direct link between experiment and theory that I kind of alluded to at the beginning. And so just to finish, I've listed kind of the main references from the paper for the different kind of papers that I've referred to here. Just want to highlight a couple of collaborators, so particularly Anna Ray Goots, who's been involved in kind of all these examples, particularly also Natalie Fernando, her former PhD student, did many of the measurements. And then in the gallium oxide side, there were lots and lots of people involved in this paper, so I can't highlight everyone, but Joel Varley, for example, did some of the calculations that I mentioned. And then just to thank EPSRC for funding and Archer for compute time.
Brilliant. Thank you very much, Laura, for a really